Hello, ladies and gentlemen. My name is Lorenz Meyer from the Technical University of Munich, and today I'm going to present you the results of my paper, Parameterized Data Handling for Forming Tool Tryouts. So let's begin with the motivation. On the right-hand side, you can see a typical tool tryout process, which is iterative. Starting with a tool geometry, the aim of this process is to get a production tool. This can be done by simulating or manufacturing. And as most of you know, this process is cost and time intensive. So what is missing is a tool that proposes a compensation strategy by using simulation data as well as manufacturing data, because the simulation data, which is generated initially, is often not considered anymore if the tool tryout process is happening in front of the press, because then typically this process is done by experienced employees, and as already mentioned, the previously generated data is not reused anymore. So let's start with a virtual tool tryout process. And in the next step, I'm going to present you the target geometry that I used in my study to generate a tool geometry, doing simulations, a deviation analysis, and compensation until we get a production tool. So this is the target geometry you can see on the right-hand side, with a length after the forming process of around about 160 millimeters. And a depth of around about 50 millimeters. And it's a very simple deep drawn part, but here the radii R6 here and here are typically used in the automotive sector. And on the right hand side of this part, we have a spline constructed part. Why a spline constructed part? Well, because the reverse engineering I'm going to present you is done by B-Splines. And I wanted to investigate if this reverse engineering using B-Splines has any advantages for spline constructed part, or if it's better for radii R6. So this is why I have two different parts, and not using, for example, an U profile. And the material under study in this case was a DP800. So after designing the target geometry, we have a tool geometry automatically designed by Autoform and a simulation using Autoform as well. And this gives me a workpiece geometry. And in the next step, I exported this workpiece geometry as an STL file and did a reverse engineering. So let's begin with our target geometry. The target geometry was exported by CATIA as an STL file as well. And here in red you can see discrete points. These discrete points were added continuously through the arc lengths of this part here in the Z and Y axis. And the reverse engineering approach was to add control points and redesign or get a representation of my part in continuous data using a mathematical description, using the mathematical description of splines. And therefore I did a spline approximation. Here you can see 12 control points that are representing the blue line. And you can see we have deviation here and here in this part. not so much here in this part, but of course it wasn't satisfying. So we added some more control points. Here you can see the reverse engineering with 35 control points, and here you can see the reverse engineering with 70 control points. Probably this this reverse engineering with 35 points already is very satisfying, but through that we have a 2D problem. It doesn't make any difference to add more control points because the memory required is still it's still very little. So let's say this is our approximation for the target geometry that is satisfying the process. Then we have a master knot vector and a master curve degree, which was 3 in this case, and 70 control point coordinates. In the next step, I used my STL file after the springback generated by Autoform and reused the master knot vector and the master curve degree and just shifted the control points so that my geometry, my current geometry was represented. And it looks like this. In blue, we have the target geometry, and in green, we have the current geometry after springback. So we don't generate a new knot vector, and we don't generate a new, or we don't change the curve degree. We just change the control point coordinates that are representing the target geometry after the springback. Now we can we have a deviation analysis as you have seen before, and we need to compensate and generate a new tool geometry. And therefore I proposed a new method called the control point compensation, which is using just the control points as geometry parameters. And the aim of it was to minimize the deviation between the target and the current geometry after springback. So the approach of the control point compensation is to calculate the vector between the control points with the same indice. For example, shown here for control point number 5, 1, 2, 3, 4, 5. And we have this vector here. And as common in the compensation, we add a compensation factor alpha and multiply it with the inverse vector. Doing this simultaneously for all the 70 control points gives us a new geometry, as shown here. In red, we have a new tool geometry. So this was just a small part of our geometry. Here you can see what I have shown you before. And in red you can see the new tool geometry for the whole part, as well as the current geometry and the target geometry. And this in red is shown in red tool geometry is reused for a new simulation. So this is my iterative tryout process. And since this reverse engineering is using splines, it's very easy to transfer it into CATIA, for example, to generate this new tool geometry. And this process can be done for numerous iterations until our deviation analysis shows us that we are within the tolerances and we get a production tool. So let's take a look at the results. here on the left side in the false color image, you can see our initial problem. And as you can see here, the drawing depth isn't reached because it's in red, so we have a deviation of around about 1.70 millimeters. As well, we have angular deviation here at the edges of the component, which is resulting through the springback of the in the radii. And this initial problem was used to compare the control point compensation with two different alphas, and was used to compare it with in the outer form implemented compensation method. So here you can see the mean deviation in Z and the iterations for our control point compensation with an alpha equal to 0.8 and an alpha equal to 0.5. As well as shown in red, the outer form compensation method. And here you can see with outer form, within 4 iterations, we reach a minimum deviation in the Z direction. Meanwhile, for the within the first iteration for our control point compensation method, we increase the problem a lot. But after that, here shown in blue, we are continuously decreasing our problem. So that shows me that the approach is working, but we still have an initial problem that has to be further explained or further investigated, because right now I have some ideas, but I can't explain it. But let's take a look at the spline representation, or the results of the control point compensation with an alpha equal to 0.8 after 7 iterations. And as you can see in this image, we nearly don't have any deviation, neither here in the radii nor here in the spline part. And here in this false color image with new boundaries, as you can see here we have new boundaries. We have the outer form compensation after 4 iterations, and as you can see the drawing depth is reached, and the deviation here in this part has decreased a lot. Here the false color image is using the normal direction to show the deviation. But after the reverse engineering, I calculated the average deviation as well in Z direction and compared those deviations to each other. So after the reverse engineering with outer form, we have a deviation of 0.0877 millimeters, average deviation. And within 8 control point compensation iterations with alpha equal to 0.5, we have a deviation of 0.0748 millimeters. Compared this to our control point compensation with alpha equal to 0.8, we get even less deviation in Z direction with 0.0705 millimeters, which was the best result in this investigation. But now let's take a look to the data consolidation. Through that we use a mathematical description, we need less storage and have continuous data. And through that we just once generated the knot vector and saved the curve degree, we can reuse this not vector and the curve degree in each iteration, which is minimizing the needed storage as well. And here you can see the memory required for the 8 iterations with the control point compensation method. Doesn't matter if the alpha is 0.5 or 0.8, because we just need to save the control point coordinates in the y and z direction. We need just 21 kilobyte within 8 iterations summarized. But compare this to the autoform compensation method by just saving the STL exported files after the springback. We need more than 3 megabyte to save our data. And I've shown you the part, which is a really small part, like this. If we're going to use this approach for example, a door of a car, you can imagine the main advantage of this representation method. So, so the mathematical description needs less storage, and it facilitates the derivation of a tool reworking strategy because of we are already using a language that is that our CAM programs, for example, are using as well, the B-Splines. So let's come to our conclusion. With the control point compensation method, we were able to compensate our our geometry and the required memory compared to the autoform compensation method was reduced by a factor of over 145. And through that our input is an STL file, we are able to use this control point compensation method for both simulation and measurement data. And as already mentioned, due to the B-Spline representation is already in the CAD language, it's very easy to reuse this data for designing a reworking strategy of our tools. So thanks a lot for your attention. If you have any questions, feel free to ask. Thanks a lot.